All right. Where did we leave off? Did we finish 28?
We got to 25, I believe.
25? Okay. Done. Does anybody need one? Who's got one? Yeah, addition to the reading. That's my last one. Nobody else here. All right, everybody's got one? Cool. Okay. Number 28. So 25 was the Van Allen belts, right? So very important. Magnetic fields, Earth's poles, all this kind of stuff. What are they protecting you from?
Solar wind.
Solar wind. Good. Solar wind. So number 26 is solar wind. No, I do not. I don't know what happened on mine. So we have a pencil we can loan this gentleman. Pen or something? Let's see if I got one in my office. I think I would.
I have one, but it's driving rainy.
Missed yesterday.
Oh. Yesterday.
Anybody else need a pen?
You sending him now?
Anybody else need a review sheet or a study guide? You got one?
Yes, sir.
It's good? Good? Well, that's my last one. So, well, what's the question?
You said that.
Yeah, I don't have one now, so you got to tell me what is it.
Now, where can you see that it is working?
Yeah, so take a look at this, right? So here's the Earth, and you know these belts of radiation, they're all coming from two spots, right? What are those two spots? North and South Pole, right? And so the whole thing is it's a magnetic field. It's charged. You've got these charged particles coming at you on the solar wind. They're interacting with the Van Allen belt, and they're getting pulled to these poles, right? So that's where you will be able to see it. What does it look like?
Northern Lights, right?
Northern Lights. Northern Lights. Let me see the question. Just what that question says. It says, where can you see that it is working? I mean, literally you can see it. Yes, sir? You can? Oh, thank you so much. Appreciate that. So, literally you can see it, because what happens, you don't have to know this right now, okay? I'm going to show you in case you were ever like, hey, what's actually going on there? Let's say you got a hydrogen atom, okay? You got the nucleus here, okay? You got an electron that's going around it. The electron wants to be as near the nucleus as it can. That's where it's at its absolute most stable. If it gets more energy, it can't stay near here. If it were to get hit by one of these subatomic particles or solar winds, you know, everything flying off, it hits this electron, it gets way too excited, and now it can either possibly fly off. That's what's going on in the sun. That's why it's plasma, not gas. There's too much energy for it to stay near the nucleus, and so it's just all over the place. Or what happens in an atom is it gets excited, and it goes to one of these higher orbitals, but it's not stable out around here. It's got too much energy. Very quickly, it's going to give that energy back off and come back down. To get rid of that energy, it has to shoot off a photon of light. And we can see these, right? And so literally what's happening here is the solar wind is hitting, it's getting drawn, it's interacting with elements in our atmosphere. The electrons get excited, they go out to higher orbitals, they can't stay there, they fall back down, they emit light, and we see greens and reds and violets and all these beautiful colors, okay? That's at the physical level, this is how the northern lights work. Okay? All right, what's the next question here? Explain how the northern, or excuse me, explain how the Van Allen belts work. Well, what's making them work? Yeah, so it's magnetism, right? The Earth's rotating, we get these magnetic field lines, and then they interact with the solar winds. They draw them to the poles. That's probably the main thing, right? So magnetic poles. I'm being very brief here, okay? Magnetic poles, charged particles these get pulled to the poles. That's the gist of it. I gotta get some markers. Next page, 29. What layer of the sun? You guys are, I didn't show you this picture. So I'm just going to tell you this picture. In this picture, everything is black except for that thing that's gray, and in the real picture, that thing that's gray is red. So if you see everything black during an eclipse and a red ring, what is that layer of the Earth that gives you the red ring, or layer of the sun? Chromosphere. Good. So what layer of the sun is clearly visible in this picture of an eclipse? It's the chromosphere. Number 30. 30 is that drawing that I told you must know. Okay? And so you can tell right now, this is what it's going to be like. We've got temperature. Oh, you're going to have to be able to label everything on here, okay? So you need to know this is what? Temperature. And what's on the other axis? Distance. Good. We'll label it. Right? So we've got A, B, C, D. A is photosphere. This is chromosphere. Transition period, very rapid, and then corona, which is hotter than core, which is insane. Okay? Pardon me? C is called the transition period, so this is as we're transitioning into corona. The main point here is it's heating so rapidly at that transition between the two layers. It's nuts. 32, what's the variable on the x-axis? It is distance, and y is temperature. Good. 34, you've got little black dots on the sun. What are they? Sunspots. Good. And the question is, what causes this? It's variations in the sun's magnetic field. Okay. Variations in the sun's magnetic field. Number 36. Where in the sun does nuclear fusion occur? It's in the core only, right? That's our sun, anyways. Yes, sir. 35. Oh, it's variations or changes in the sun's magnetic field. (36) Where in the sun does nuclear fusion occur? That's in the core. 37. What is the hottest layer of the sun? Corona. Good. 38. little bit of a trick question. Why does the corona get so hot as it gets away from the core of the sun? We do not know. We have no answer for this. Defies logic and everything else we know. Good. 39, which layers of the sun can we actually see? We can see the photosphere and chromosphere and corona, right? Can't see anything below that. It's too dense. Photosphere is too dense. Let me draw it. First layer is core. Second layer is radiated. Just goes out, right? Next layer is convective. Good. Can we see any of this? No. Because the next layer is far too dense. It's the one that produces the light that we can, or emanates the light that we can see. What's it called? Photosphere. We can see this. Photosphere. The next layer is the red layer, right? What's it called? Chromosphere. And then the last layer is corona. All those pictures you were doing with as a kid of the crazy sun, you weren't that far off, because it really does kind of flare out like that, right? So this is the corona. You don't see this well, but you can surely see it during an eclipse. You don't really see this at all except during an eclipse, but you can visibly see it. It's not hidden from you. It's just that this is so stinking bright, right? But you cannot see these inner layers because of how dense and bright that photosphere is, okay? All right. Yeah, so 39 and 40 are, two halves of the same thing. Basically everything in here we cannot see, everything out here we can. It's 3 and 3.
What is the one with the convection zone?
Oh, it's this. Sorry, it is the convection zone. Convection, and this is radiative. Number 41, what is a star? Did you say mass? I've had several people tell me. I don't know where that's come from, but I know that you guys got it from somewhere. I don't think it was me. I hope not. I mean, yes, to some extent that's true. Like, it is mass. It's got matter, but really we need to thinking gas, giant ball of gas. Now, as I say that, let's pause for a second. The bulk of what, our sun is filled not only with gas, but plasma, right? As it's undergoing this fusion, it's so hot that the electrons can't stay around, so it's in a state of plasma, which is just an ionized gas. You start with gas, as it contracts, by the way, what force is causing it to contract and heat up?
Gravity.
Gravity, goodness. Gravity's heating that joker up, right? Cilia. Remember cilia from this morning? You were there, in class. Little hair-like structures that bring the,
Yes,
okay,
sir.
all right. That would have been really great if you paid any attention. So, anyway, I lost my way. What was I talking about? No, I wasn't talking about cilia. All right. Yeah, gravity heating it up, and the gas will turn into plasma as it gets hot and the electrons get stripped off it. Okay. So it's a giant ball of gas. That's like, if you want full credit for that, you must say that. This is a question, you give me more than I'm asking, I'll give you extra. You want to tell me that it's doing fusion in the core? Awesome. You want to tell me it's plasma and gas? Awesome. You know, you could go even further, but you know, you probably don't know enough for that yet. So, at minimum, you can tell me it's a giant ball of gas, right? Ideally, you'll tell me also plasma and fusion. I'll give you extra. I'm all about it, okay? 42. Which two elements are stars primarily made up of?
Hydrogen.
Hydrogen and helium. Good.
You want us to put like that element spelled out? Or
I'm cool either way, man. Yeah. I'll know what you're saying. Number 45, which phase of matter? Oh, I'm sorry. I skipped stuff, didn't I? We're on number 43. Everybody good to go on to number 43? Okay. Number 43 shows you a picture. It's a picture of a comet. What happened to that comet's tail? What caused it?
The solar wind.
Solar wind. Solar wind is literally blowing that comet's tail off into these striations. It's really the only way we can visually see solar wind. We can measure it to a certain extent as the particles come into our atmosphere and stuff like that. But to see, you know, it's like how you see the wind. You can't see the wind, but you can see the wind like blowing stuff, you know. Same thing here. All right, 44. Why do stars initially get hot enough to start nuclear fusion? Well, we actually just did that, right? So what is it?
Gravity.
Gravity. Gravity, force of gravity. No, 45. Which phase of matter is found in greatest abundance in the sun? It's not gas.
Plasma.
It's plasma. So you have a 50-50 shot, right? It's plasma. Okay. 46. How do scientists describe this phase of matter? So how do scientists describe what plasma is? I've said this several times. Ionized gas. Now, if you write ionized gas, you're going to get it right, and I'm going to give you credit. And if you memorize that, good, you got it right on a test. But do you know what I mean when I say ionized gas?
Yeah. It's an electric proton.
So let's go back to this hydrogen thing, right? So I got this hydrogen nucleus, which, by the way, is just a proton, right? Okay. So I got a proton. Proton, what's the charge?
Positive.
Positive. What's attracted to it? An electron. So under normal circumstances, if I got a proton and it comes anywhere near an electron, that electron is just going to be whizzing around it, right? That's a gas. It's hydrogen gas, right? And actually, in normal conditions, it's going to be two hydrogens bonded together. Here, diatomic hydrogen gas. So this would be normal. And since all stars begin as just gas, they're all beginning with these. But when they heat up, we're adding energy. Remember, I said when the solar wind hits hydrogen or oxygen or anything else in our atmosphere, how it kicks off an electron? Because it gets too much energy, and the electron has to like whiz around really far. And if it really got too much energy, the electron would just be lost, right? Well, that's what happens here in the sun. As gravity is heating everything up and it's converting from a gas to plasma, it's too hot. There's too much energy in the system for the electron to stay around that proton, right? And so it can't. And so the electron now is just flying around on its own, independent of this proton. Okay? The energy that this thing has from heat is greater than the force of attraction, electrostatic attraction between a proton and an electron. And so it will not just go around it. Well, just thinking back to chemistry, if you normally in most atoms, you have the same number. If you were to look at it and go, oh, it's got 5 protons. Well, how many electrons does it have? Say 5. Say 5. It has 3 protons. How many electrons does it have? Say 3. If it has 2, it should have 2, because opposites attract. If we got 2 positive charges, I'd expect to have 2 negative charges. If I had 5 positive charges, I'd expect to have 5 negative charges. But with an ion, there's an imbalance. You've either gained or lost an electron, right? And so when we say that plasma is ionized gas, we're saying, hey, it's so hot that this thing's flying off on its own, and this atom has a charge. It's an ion, okay? It's so hot that this can't go back to just being a gas. It's being an ion. So that's why we say that plasma is ionized gas, okay? I hope for you that you'll, I mean, you encounter this term, right? You just got 4 phases of matter. You've heard plasma all your life, but no one's ever explained to you what it was, right? You're here in East Texas, maybe you're from London, maybe you're from Jacksonville. If you're around anybody from East Texas, you know somebody who welds, and anybody who welds also has a plasma cutter. So they feed acetylene and gases into this, and by very definition, you're starting to go like, oh my goodness, they're heating that gas up so hot that the electrons can't stay around it. And it's forming plasma in this little tiny thing. That's crazy hot, right? So, and maybe you're gonna go home and, or to your dorm or whatever, and you're never gonna think about this again. That's cool too. But I gave you a shot, okay? That's all I got on this. Do you have any questions? Okay, I'm gonna shut